Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside. We are doing section 10.5 in the Big Ideas Math Integrated Math 2 textbook on angle relationships and circles. Now, we just came off of section 10.4 with inscribed angles, and if you don't know what we did with inscribed angles, sorry, I have a stuffy nose today. If you don't know what we did with inscribed angles, I recommend you check that one out or you study up on that stuff, because the formula they use there will be a formula that I emphasize for the formulas we use here. I don't know if the book is going to be using the formulas in the same way. I know that they go more off of proofs of things, and mine isn't so much a proof concept, but more of a logic concept, and I'm going to follow up with that if I feel like the book is not going to. So strap in for that. We're going to do a lecture on this stuff and the problem set. Let's go and take a look at what we have as I clear a sniffle. Give me one moment here. Okay, yeah, this is going to be a tough one. We'll see. I always need to devote days to this stuff, and sometimes when allergies kick in, I just can't do anything about it. All right, we're going to learn to find angle and arc measures. Not that we haven't done it before, but just in a general sense with all kinds of circles. And use circumscribe angles. Oh, I know what those are. Use circumscribe angles, and that is the core vocabulary word as we talk about tangents, chords, and secants. For me, the big vocabulary word as an overall is inscribed angle. So if you remember what inscribed angles were, like this one right here, an inscribed angle, boom, boom. Everything I do is going to be based off this concept. If you recall, the inscribed angle is half the measure of its intercepted arc, like that. Keep that in mind for the things we're about to talk about here. All right. There are different theorems with different visuals, but they all have the same meaning if you think inscribed angle. Tangent and intersected chord theorem. I'm not going to remember that name, but here we go. If a tangent, I get it. If a tangent and a chord intersect at a point on the circle, not a radius, then the measure of each angle formed is half the measure of its intercepted arc. Now, the important thing is noting what intercepted arc you have. Here, I have this angle, and its intercepted arc is right there. Now, the way we should understand intercepted arcs are, they are the arc's endpoints are the same as the angle's endpoints. Now, this angle's endpoint is right there like its arc, just like this one would be. But this one's a little different because it's not on a part that's outside of the vertex. This part on the vertex is the same as the intercepted arc part. So this angle even still has a point on its angle that's the intercepted arc's endpoint, so that still makes sense that it's there. Likewise, on the other side where you have this ABC guy, this intercepted arc is for this angle right there. The vertex is still that point, but it's still half the measure. Much like this guy, or this angle is half its intercepted arc, you can still think of this like an inscribed angle. Let's say I took this one right here and moved it like this. We still have the same idea. That's still an x, and this is still that 2x, right? So just moving it there, it's still an inscribed angle. This angle is still on the circle, and its endpoints still meet at its intercepted arc, and that still works exactly like this. No change. No change. So they have some examples here. Line M is tangent to the circle. Find the measure of the red angle or arc. So let's find the measure of this red angle. Think of it like an inscribed angle there with the intercepted arc of 30. This one is half of the 130, which is 65 degrees. And if it helps, things are mostly drawn to scale in the book, or at least the idea of it. One looks like an acute angle, less than 90 degrees, so 65 makes sense. It wouldn't be 130. That would be obtuse looking. You can't go by things drawn to scale, but if we're going to make sense of it right now, feel at the scaling, it makes sense that 65 degrees would be what it is. In this one right here, we have that inscribed angle of 125 degrees. The intercepted arc would be double that measure, which would be 250 degrees. And that makes sense as far as scaling goes with this thing as well. It's more than a semicircle, and 250 degrees is more than 180. So I'm good with that as well. Sniffle pause. All right, at this point, I think I'm just going to sound congested. Apologize for that. They have a few more. I'm not going to write anything. Measure of angle 1, half of that is 105 degrees. RST is this guy, so doubling the 98, you get 196 degrees. Measure of XY, this one is the opposite side of it, so you can either double this to get 160, subtract 360 minus 160 and get 200, or find its supplement as a linear pair of 100 degrees, double that to get 200. Oh, XY, I'm sorry, they wanted the minor arc, so 160 degrees. Okay, there it is. All right, let's go to this one, and I think this is where I want to navigate some things more. I feel like the book's not going to talk about it because they're only going to do it in a proof format. So let me hide away this number page for a second, or page number. If two non-parallel lines intersect a circle, there are three places where the lines can intersect. Oh, they're not doing the formulas yet. There are three places where it can intersect. But this first one is super important, on the circle, right? If you're on the circle, this is where you can feature, say, an inscribed angle, which is half the measure of its intercepted arc. Remember that, obviously. It can also intersect inside the circle, and it can intersect outside the circle. Now, that's not a very extreme outside the circle. They could be more like this as well. That's not even that extreme. They can do some extreme ones that I'm sure you're going to see pictures and examples of. But the intersecting point doesn't always have to be on the circle. But there will be formulas for all three of them, and we want to make sense of all of them. We should know the first one. Let's move forward to them talking about it. If two chords intersect inside a circle, then the measure of each angle is half the sum of the measures of the arcs intercepted by the angle and its vertical angle. They're talking about this guy and this guy right here. When we add those two together, we take half of the sum of these two. That'll equal either angle measure 1 or its vertical angle. And 2's angle measure will be half the sum of this guy plus this guy. Let me do a sniffle thing again, and I'm going to talk about a proof. I'm going to construct something in my pause. Okay, so in pausing, I also constructed this thing. I want you to take a look at this, and I want you to think about this. All right, and also I need to write a number here. Let's call this an X. Okay, this is an inscribed, the way that I currently formed this is made to be an inscribed angle, and I hope you agree that this angle right here on the circle, and then I'd have this guy, I'll put in blue right here. I'll call it 2x right there. That's double this, right? Half the measure of its intercepted arc. When I move this angle around, pick it up and move it, it doesn't change the angle, right? Just changes where it's moved. So let's say I slid it this way like that. Okay? I take that and slide it inside the circle. The angle measure didn't change, right? But this intercepted arc did. This is no longer actually 2x. I should actually get rid of the 2x portion of this. That's no longer 2x. It got smaller. It got smaller. How much smaller did it get? It got this much smaller right here. What was here before is now lost in the angle. And we have no idea where that endpoint can be found. Do you know where we can find this arc measure? How about over here? What was lost in the other part of the angle here, what got erased, what was lost, has now been gained on this side. This plus this is the original this right here. That original 2x is now formed over these two angles now made right here. So that red plus blue, I don't know how else to put it, red plus blue equals 2x still. X is half of red plus blue because it's still half the measure of what its intercepted arc measure would be. That's how I want to make sense of this. This thing is no different than the inscribed angle formula. It takes your inscribed angle, moves it inside the circle, and what is lost in your intercepted arc is gained on the other side. So you add those together, and that becomes what would have been the original intercepted arc. Or treat it as the way of if you take this and slide it out from here, make it an inscribed angle, then what is lost there is now gained here, and we know an inscribed angle is half the measure of its intercepted arc. Either way, you can think of it like the inscribed angle formula, and you're good to go. And all the formulas we do based off this will be the exact same. The idea, what's lost is gained here, what's gained is lost here as we move it. All based off inscribed angles. So know that formula, you should be good to go. Outside the circle, and here's where it's more extreme outside the circle. So take a look at these ones. They all have the same idea. If you take half the difference of this bigger arc minus this smaller arc, this angle is half of this minus that, and this angle is half of this minus that. Every part of an arc that is captured inside of your angle measures, it's one minus the other. Why is it subtracted, Mr. Robinson? Why are we taking away from? Let's go back to our example up here. And remember, I treat these all three the same. They say a tangent and a secant, two tangents or two secants. They're all the same. They're outside of the circle, and they are ones of which, yeah, they're all outside of the circle. So look, listen, it's the same concept no matter what. Let's pull this one back. Let's pull this one out a little bit. What's happening to my intercepted arc here? The intercepted arc grew larger. How much larger? This much larger. Compared to the original inscribed angle, it's now gotten this much larger. Where was this much larger? Where can we also find this much larger from the original? Oh, I don't know. Maybe right here. Maybe right here. Right? That part that was gained is also gained on this side. So the original blue that would have been my original inscribed angles intercepted arc, half the measure of that, that's still here, but it's now take this and take that out. Take away this, which means you take away this as well, and you're left with the blue. So now it's, you can ignore what I wrote for the 1/2 red plus blue now, but now it's a subtraction bit because this got bigger and we got to take that amount out, what's gained. So it doesn't matter if it's that or if it's the secants or whatever, right? Secants, tangents. It doesn't matter if it's secants or tangents, it's one minus the other, but it's still half the measure of what would have originally been an inscribed angle. So let's go back to that idea. Let's take this, bring it back to where it originally was, vertex-wise, move it into the blue, move it as an inscribed angle. Look how much was lost here and how much was lost here. Now we're back at that blue. If you want to get that 2x, whatever's gained here, you got to subtract out. And that's how we reason with these formulas. That's my best go about with that. You have to accept the visual for what it is. It's not a proof. But you have to accept the visual for what it is and understand inscribed angles for it. And I know I spent 11 minutes talking about all that, but I hope that that explanation can now be utilized, even though I'll probably do proofs for the problems. Okay, some examples. We're going to find the value of x. X will be half the sum of 156 and 130. So we add those up, divide by 2, you get 143. Let's find this x. This x is half the difference of this 178 and 76. 178 minus 76 is 102. Half of that is 51. 51, and that's that x there. Some other examples here. In some of these ones, you'll notice, I'm not going to do them, but you'll notice that this time y is one of the arc measures. So 102 is the other angle here. You have to find this angle measure by the supplement, linear pair, and it'll be half of y plus 95. So there are some values, some problems where we're going to have our variable inside the parentheses in the 1/2. We'll just double some things and go from there. It'll make a lot more sense when we get them done in the practice problems. Okay, here's a circumscribed angle. You saw it with the two tangents. It's an angle whose tangents are sides are tangent to the circle. There's a theorem. The measure of a circumscribed angle is equal to 180 degrees minus the measure of the central angle that intercepts the same arc. I normally say it the other way. I normally say that these two are supplementary. These two add to 180. If I said x and y, I'd say x plus y equals 180. And they're good. What they're doing is they're now subtracting that y over. X is 180 minus y, basically, like that. They wrote that right here. I tend to call them supplementary because what you're really looking at here as well, if you think about it, is you have a quadrilateral. Quadrilateral sum is 360 degrees. But if you take away this angle and this angle, what's left? Well, this is a radius with a tangent. That's 90 degrees. So is this one here. So what happens when you take away two 90s from 360? You get 180. You get 180. And that's what's left there. Now I got to sneeze. I don't want to sneeze in the mic. Hold on. I dearly apologize. This is not a good time to record this video. I hope it's not detractory to your learning experience. I know the pauses are there, but still, I just sneezed. All right, find this value of x. So again, the way I'd say it is these are supplementary. X plus 135 is 180. So you subtract 135 from 180, and you get 45. So that's x's value in this one. In this one, it's going to be a little different. It's not the central angle that you have here. It's an inscribed angle. So what you can do, you can find out what the central angle is for this. I don't know how they're going to do it. You can find out the central angle for this. 180 minus 30 is 150. If this is 150, then its intercepted arc is 150, which means the inscribed angle for that intercepted arc is half of that, which is 75. So let's see if they do the same thing. They say find the central angle first and go off of that. That's kind of what I would do. They do that. So they take it. Oh, or they go. Yeah, that works. So 180 minus the measure of EHF. Where's H? Oh, this one, the EHF. But they do the 1/2 part, right? Because the idea is half of the intercepted arc that you have there. So it's still 75 that you get either way. Pause one more time. Yeah. What's funny was I was going to record this a lot earlier in the day, and then I had a 2-hour phone call to take care of, so that didn't help. All right. Let's see what they have here. Modeling with mathematics, some real world problems. The northern lights are bright flashes of colored light between 50 and 200 miles above Earth. A flash occurs 150 miles above Earth at point C. What is the measure of arc BD the portion of Earth from which the flash is visible. Earth's radius is approximately 4,000 miles. So they have some things drawn. 4,000 miles, and because it's 150 miles above Earth, you take the radius here, 4,000, and add an additional 150. So we have 4,000 here and 150 there. Now, the points, I don't know what this has to do with our inscribed angle stuff, but the measure of the arc, I don't know. But the points, I don't know what this has to do with it. The northern lights point, I guess, is tangent to this part of the Earth where things can be seen. So we're looking at this being maybe a right angle. So then we can use maybe Pythagorean theorem to work things out. Let's see what they say. Given the radius, you find the measure of the arc. I would have said, yeah, I would have done inverse tangent. Do they do that? Because there are tangents, they're perpendicular. These are all tangent theorem. These corresponding parts of congruent triangles are congruent. Solve the right triangle. Okay, yeah. So they're using inverse. It looks like here they say inverse cosine. I would use. So here's what I would do. So I'm not. They're reading some things out without showing the math. I'd find the measure of this angle here because I can double it. This is the central angle, and then I'd find its intercepted arc measure once I double it. To find this angle measure here, what I would do, yes, I would use inverse cosine. Inverse cosine of A, 4,000 over 4,150 is the measure of A. Then I would double it. That would be the central angle, and then you get the entire thing from that. So in a right triangle, because this is a right angle here, in a right triangle, 4,000 is adjacent, 4,150 is hypotenuse. So inverse cosine of 4,000 over 4,150 is that angle. They're going to double that. Exactly. So I don't know what they were saying for all this 31 stuff. They said they use some other stuff for that. I'm going to go off this one. I like the inverse trig version. You get about 31 degrees when you double it. Okay. More examples there. I'll leave it. Okay, let's go to the problem set. So hopefully some of the stuff I explained made a lot of sense with the inscribed angle things. That's how I make best sense of the formulas. I will never forget them. As long as I know the inscribed angle thing, I will never forget those ones. I hope you don't as well, because you don't try to memorize and mismemorize and stuff like that. Let's start with these two, vocabulary and core concept check, then we'll go to the core problems. Complete the sentence. Points A, B, C, and D are on a circle, and AB intersects CD at point P. If measure of angle APC is half the measure of arc BD minus arc AC, then P is blank the circle. It'll be outside the circle. Now, the only reason I can say that without needing to draw it is because in the formula they're mentioning a minus here. But let's get an idea of a drawing. I have a circle, and I have, I guess B and D are next to each other-ish, and A and C. Sure, we can work that. The angle's going to have to be outside to work this kind of formula. This is some point P. This would be your 1/2 measure of arc BD minus measure of arc AC, and that's outside of the circle for that to happen. Again, we lose all of AC to stuff. I talked about that before. All right, writing. Explain how to find the measure of a circumscribed angle. So the circumscribed angle is the one that is actually on the circle itself. What I like to say is that it is supplementary. A circumscribed angle is supplementary to a central angle whose radii intersect with the tangents, or with the sides of the circumscribed angle. So if they're supplementary, you find its measure by solving for it at that point. If they're supplementary, they add to 180. So you subtract your measure from 180. That's what you could say. Subtract the central angle's measure from 180. But I like that setup first. All right, we're going to look at some of those problems there. In order to do so, first see my face, and then I say, hi, how you doing? Check out the timestamps below if you want to find what you're trying to find from this PDF. Very much apologize for my allergies. Let's go ahead and take a look at what we got. Let's start with numbers 3 through 6. Line, let's pop this up. Line T is tangent to the circle. Find the indicated measure. So you can treat these as inscribed angles. I want to find the measure of arc AB. A lot of times I'll be playing with stuff on the screen over here. Arc AB is this guy. 65 is, in essence, an inscribed angle with this intercepted arc. So we're going to be doubling 65 to get there. 65 is half its measure. We double it. We get 130 degrees. Number 4. Find the measure of arc DEF. Once again, DEF being this guy, it is the intercepted arc for that inscribed angle of 117. Yes, I can call it an inscribed angle in the same way that an inscribed angle would work. It's half that measure, so we get to double the 117. we get 234 degrees. Number 5, measure of angle 1. This is the inscribed angle, half the measure of that intercepted arc, 260 degrees. So we are going to take half of 260, and we get 130 degrees. My type font stuff I got off my calligraphic pen. Number 6, measure of angle 3. So you have two different options here. Measure of angle 3. You have two options. You can either do half of, see, the 140 is this angle, or this arc right here. I need to find that arc. So if I find that arc, I can take half of it. How do I find this arc? Got to subtract 140 from 360. So I can do 1/2 of 360 minus 140, which is half of 220, which is 110 degrees. Or you can do 180 minus half of 140. And I bring this one up. So what I'm saying here is this. 3's angle measure is a linear pair with this angle measure. Whatever this guy is, these two add to 180. So if I find the inscribed angle for this 140 intercepted arc, half of that is 70, then this is the linear pair with 70. So we take half of the 140 first, and then we subtract that from 180, and we still get 110. So you can either find the other guy's inscribed angle first or the intercepted arc for 3 first. Either way, you still get your 110. All right, let's move on to number 7 to 14, where they ask you to find the value of x. These drawings can get a little complex looking, but they all have the same premises in mind, as long as you understood the inscribed angle stuff I talked about at the beginning of the lecture portion. I don't know if it's the beginning, but somewhere through the lecture. This x, angle measure, is half the sum of these two angles, 145 and 85. It's not a central angle, it's not an inscribed angle, but if I treat it like an inscribed angle in such a way that it's half of that intercepted arc measure, in this case the sum of these two, then you're all good to go. So this is half of, and if you didn't watch the lecture portion of my video, you don't have to watch the whole thing. I do want you to find the part where we talk about these kinds of formulas and how I justified why this one's going to be a sum in this case, and why in some other cases it might not be. This should be 115 degrees when it takes half the sum of those two. Number 8 is also going to be half the sum of some things. However, this time x is the other, it's a linear pair angle measure thing. So for example, maybe I find some angle y first, right? X is just going to be the linear pair with it. So you don't always have to call it a y. You could call it 180 minus x. I'm just going to call it y this first time, and then you'll understand how I justify calling it 180 minus x in a future problem if we have to do that. So x is 180 minus y, right? So, okay, so y is going to be half the sum of 2x minus 30 and 30. Negative 30 plus 30 is 0, so we're just going to be half of 2x, which is x. So y equals x. Oh, this is interesting, because there's an x that's there already. So let's turn, so y equals x. That's weird, because now I'm going to have an x here. X is 180 minus y. So x is 180, what am I doing? Not 1/2. X is 180 minus y, which is now, if y equals x, that's 180 minus x. So x is 180 minus x. Sorry, this is really weird. Add x to both sides and divide both sides by 2. You get x equals 90. To the right angles. Yeah, I probably would have started, instead of writing y, I could have started with 180 minus x, and it would have still brought out that stuff. You would have gotten basically to this stage right here. This is the important part to get to, and then we solve for x from there, and that's what we get. All right, weird problem. Number 9. This time, we have the intersecting part outside the circle, so we're going to subtract two measures. Not the inscribed angle, but this angle with these intercepted arcs, this will be half the difference of this one minus this one. So 29 degrees, not x, but 29 degrees is half the measure of the difference of the bigger arc minus the smaller arc, and x is that smaller arc. Now, instead of distributing 1/2 here, the better bet for this every single time, and I won't write this in future times, but multiply both sides by 2. You have the 1/2 here. If you multiply by 2, that part goes away, but we double this angle measure here, the 58. 58 is 114 minus x. If I add x to both sides, and subtract 58 from both sides, then I can, whoops, get my result. 58. And that'll be 56. X is 56. All right, number 10. It's a lot of stuff. X plus 6 is right there that they're pointing to. That's a part of that arc. 34 is the angle measure. So 34, the angle measure is half the difference of, I got the bigger arc as 3x minus 2. 3x minus 2. And then I got to subtract the smaller arc, which says x plus 6. So one minus the other like that. Now you really want to use quantities in parentheses here, because when I subtract, I have to distribute the negative into both of these. I will be doubling. I'm going to double both sides. The 1/2 will be gone. I'll have 68. 68 here. But 3x, let's write it this way. 3x minus 2 minus x minus 6. Now I can combine things. 3x minus x is 2x. Negative 2 minus 6 is negative 8. Let's keep solving for x. I'll add 8 to both sides and divide both sides by 2. I get x equals 38. I'm not double checking these, but it's looking pretty good from here. That's number 10. Number 11. 11. Okay, all these things involve x. That angle will be, this angle here will be half of this minus this. So let's just write it out that way, x over 2. I like that that says over 2, because when I double it, it'll just say x. It's half the difference of, let's do that again. Half the difference of x plus 70 minus, oh, interesting, x minus x plus 30. Looks like these x's here will cancel out. So I'm going to do two things in one. I am going to multiply both sides by 2. Those 2's will be gone. Now it'll say x equals x plus 70 minus x minus 30, distributing the negative, and x minus x is gone. And now you're just left with 70 minus 30, so x equals 40. Unique problems. You know, what's interesting is the examples. Maybe the examples did do it, but I skipped those monitoring progress questions, so I didn't see them. They didn't lead them with you, but I could have. All right, this one's quite interesting here, number 12. They have 6. So check this out. We'll do it practically first, and then we'll talk about what it means. 6x minus 11 equals half of, they didn't give us a measure here. What the heck is going on? What do I do here? Well, you can find the measure. If this is 125, then this is 360 minus 125, right? 360 minus 25 is this value. So check this out. What's 360 minus 125? I don't know, 235? 235, but we're going to subtract another 125 on top of that, like so. Okay. And then we can double both sides, and we get 6x minus 11 equals 235 minus 125, which is 110. So we had to do 360 minus 125 to get what that thing would be, and then we had to subtract yet another 125 on top of it, right, to then figure out what that was. So there was a doubling effect of subtracting 125 from there. I had more that I wanted to say on it. I forgot what I wanted to say, but we're good from here. Let's keep going. Let's add 11 to both sides. Whoops, equals, that's 121. And then divide both sides by 6. And we get x equals 121 over 6. I don't think that reduces, so I'm just going to leave it like that. I feel like that should be the right answer. I don't know. I thought that I'd just have all integer answers, but at this point, I guess that is what it is. Let me think on that one. Half the difference of that minus that. 235 minus 125. Oh, I didn't double this. I'm sorry. We have to double this. Let's do that again. I doubled nothing. I just said 6x minus 11 is 110. Let's do that again. I have to double this side. I'm so sorry about this. Times 2 and times 2. Okay. 12x minus 22 equals 110. There we go. Now we add 22. I was like, I didn't like what I was saying there. 132. There we go. Now x equals 11. Does that look better to you guys? I think that at least it's a whole number this time, so I feel a little bit better about the answer. I'm going to go with it. All right, number 13. We have two more, I think, that are like this. Number 13. So the way that I spoke about this kind in the lecture portion. Okay, so here's what we can do. We have this inscribed angle of 73. So this arc right here will be double the 73. 2 times 73 is 146. So this guy is 146 degrees, right? This guy's 146. This guy will be 360 minus 146 right here. 360 minus 146. Now 360 minus 146 is 214, I think. So 214. So our x will be half of 214 minus 146. So this time, since x is on this side, oh, you know what? I probably didn't have anything to double here. I got too big in my doubling thing from previous problems because x was in here. I didn't need to double this. I overdid my work on that one. I really feel bad about that one. So I'm going to keep the 1/2 here this time. 214 minus 146 is 68. And half of 68 is 34. Yeah, I feel like I probably should have just done the, I don't know, I got so stuck in the doubling thing and explaining that I didn't realize that I probably don't need to do it for that one. So what I probably would have done for this problem instead of multiplying by 2, 6x minus 11 equals 1/2 of 235 minus 125. I would have kept the 1/2 there. 6x minus 11 equals half of 110, and half of 110 is 55. Now I gotta sneeze again. I feel like 6x is 66 and x is 11. So there was that other one as well, which we could have done. Let me pause here in case I got to sneeze. Okay, let's keep moving forward. Let's go to number 14. Okay, and in number 14, we have 75 degrees as half of this 17x minus, now remember, this other guy right here is going to be the difference between 360 and 17x. So 360 minus 17x. And those don't combine. So 17x minus, and then boom, 360 minus 17x. Like that. So 75 is half. I probably should have doubled everything at this point. 17x minus 34x minus 360. Actually, let's take half right here because these things will, what do you say? I can distribute that. So I get 17x minus 180. Okay. So 17x minus 180, if I add 180 to both sides, I get 255. And divide both sides by 17, I imagine that's 15. It must be, actually. Yeah, I think that's going to be 15. So that's x equals 15. Okay. All right, in exercises 15 and 16, describe and correct the error in finding the angle measure. Number 15, they have 37 and 46. They want to find the measure of angle SUT. I think it should be half the sum of these two, half of 37 plus 46. They just said it was the same as the arc of 46, so they said it's that. That's incorrect unless that's the central angle, which it doesn't appear to be. There's no reason. It can't be the central angle if those are different angles there. So they found their measure the same way they would a central angle, which this is not. Another way we know it's not the central angle, it's not on the center. Look, center P is right there, and it's not on the center, so we know it's not that. So how do we find this thing? Measure of angle SUT. SUT. It's going to be half the sum of 37 and 46. So it'll be half of 83, which is 41.5 degrees. Not quite 46, close, sure, but not it. Okay, number 16. Here they took the difference between 122 and 70, which they should do, but they got to take half that value, kind of like how inscribed angles work, and they didn't. So they said it's just 52 degrees. So on number 16, they still need to take half the value. They never took. They never took half the difference. So just finish off at the end. Their first part's correct, but measure of angle 1 is half of 52, which is 26 degrees. Okay, that's 15 and 16. Let's keep moving forward. Number 17 to 22. We have this one thing here. Find the indicated angle measured, justify your answer. I wonder if finding one helps us find others, so I might copy and paste this object over. Measure of angle 1. Okay, let's bring this image over and see if this will help us at all. At least then I can do some color coding things too. Come on, there it goes. Okay. Measure of angle 1. It's this guy on the outside right here. And listen, there are a lot of ways we can talk about doing these things. I don't know which one way I want to bring about first. But what I'm looking at is how the angle extends out to here and to here. So what I'm looking at are kind of these two intercepted arc bits, like this one right here. Let's use a different color. Red is kind of already taken. This one right here. And then this one out here. Okay? So if I do angle 1 can be half the difference of this arc and this arc. That's the way I can go about it. But I still need to find what this arc is in yellow. So I'll find that out first. I got 120, 120, and 60. It's likely this is also 60. I think we can almost use that. 240, yeah. So this guy's also 60 degrees. So I know that the measure of angle 1 is going to be half of 120 plus 60 is 180. I guess that's a semicircle. This is a center. 180 minus this 60 right here. And I'm sure there are other ways I could have found that, but that's the one that catches my attention with respect to the section. So we'll get half of 120, which is 60 degrees. So measure of angle 1 is 60 degrees. Not just that arc, but also the angle. Number 18, measure of angle 2. Now, like I said, I think everything here is now therefore kind of like symmetrical. So it seems like whatever 2 is 4 is, whatever 1 is 6 is, things like that. I don't see any reason why it's not, so I'm just going to use that. So measure of angle 2, that's this guy here. Now, measure of angle 2, we can use this. 2 is an inscribed angle with this intercepted arc of 120 degrees. So measure of angle 2 is just half of 120, which is also 60 degrees. So cool, a couple 60-degree angle measures there. Measure of angle 3, where's 3? It's up there. Measure of angle 3, you got a couple options. One of them, you can look in this right triangle, and in this right triangle, I have 90, and this is 60. We just found that out. So this is 90 minus 60, which is 30. So within the triangle, so measure of angle 2, help me find measure of angle 3. You could have also said 3 is the inscribed angle with the intercepted arc of 60 degrees, and half of 60 is also 30. Measure of angle 4 should equal measure of angle 2. This is just a symmetry thing. Anything I did on 2, I could do on 4 on the other side. So measure of angle 4 equals measure of angle 2, which is also 60 degrees. Sorry for going there. Oh, I'm sorry. This is not, let's go back. That is different. I didn't see how that thing worked. I'm sorry. It's different. Okay. Now, what is measure of angle 4? Looks like it's going to be 90. So I have a couple things I could speak on. One is this is a center, so that radius is touching a tangent line. So I could say 90 degrees off of that. You could also, with the same thing as a semicircle, this is a 180-degree semicircle, so 120 plus 60. Let's do that. Let's say it's half of 120 plus 60, which is 90 degrees. Yeah, you have a bunch of options like that. I thought this was just the same thing on the other side, but I didn't see there wasn't a chord here. Number 21, measure of angle 5. Angle 5 is this little guy right here. Now, if this guy's also going to be 90 degrees, we know that 2 is 60. So measure of angle 5 is 90 minus 60, which is 30. And we could have also done that from measure of angle 1. This is also a right triangle right here, and 1 is 60 degrees, so 90 minus 60 still gives us the 30. Or the way you probably want to look at it, here's the intercepted arc. This little guy is 60 degrees for that measure, and half of 60 is 30. Remember, you should get the same answer regardless, and that looks like that's what it is. And then number 22, measure of angle 6, that one on the outside over there, that's the same thing as measure of angle 1 on this side. It should also be 60 degrees, half of 180 minus 60. So measure of angle 6, also 60 degrees. Okay. All right, let's keep moving forward to number 23. We start to hit some word problems, probably some proofs down the line. So 23 is problem solving. You're flying in a hot air balloon about 1.2 miles above the ground. Find the measure of the arc that represents the part of Earth you can see. So you can see up to the horizon, as we are not a flat Earth. This is going to bother flat Earth people seeing these problems. You're like, impossible, you can see the whole thing. Or what? I don't know what their justification is. But here's the measure of the arc we're trying to be able to say we can see. And that's going to be the same as the central angle that we have here. So my goal is to find out this whole central angle measure just by finding out one of these angle measures right here like that. So if this is 4,000, this is adjacent to this angle that I'm looking at here. And 4,001.2 is the hypotenuse for that right triangle. So in this right triangle, I want to find that angle, double it, and that'll be equal to the measure of arc xz. So the inverse cosine of 4,000 over 4,001.2 is going to be about, and I'm just going to do some rounding here. Let's use the calculator. I don't think this calculator has trig stuff on it. 4,000 or 4,001.2. It's going to be hard to find. Trigonometry. That's cosine. Where's inverse cosine? This doesn't have inverse cosine on it. Sorry, I have to pull up another calculator. Give me a second. Let me just pause while I'm pulling it up. Give me a second. Okay, I'm back. Sorry, I was first using the computer calculator and not my emulator. I'm getting around 1.4 degrees. Now that makes a lot of sense. Maybe not to scale with the picture, but 4,000 and 4,001.2 are quite close to each other in length. So that must be a very small angle to make that work. So the measure of angle, that's just one of those. The measure of angle ZYX, for example, is going to be double that, 2 1.4 degree things, which is 3.8 degrees, and it would still stay rounded to that. This is also going to be the measure of arc xz. Measure of arc xz is also equal to the central angle, so 3.8 degrees. It's approximated, but that's about as much of the Earth as you can see from that vantage point, 1.2 miles above the ground. Find the measure of the arc that represents the part of Earth. Yeah, that's not your angle of rotation. That's just the arc for as much as you... Yeah, it says not drawn to scale there. One of the first times they have that because it's so skinny. All right, number 24. You are watching fireworks over San Diego Bay. I've been there. I like that the boat is not flat earthing right now. S, as you sail... Where's S? So fireworks over the bay, S, as you sail away in a boat. The highest point the fireworks reach, F, this is an inventive problem, is about 0.2 miles above our bay, or above the bay. So 0.2 is up there. At point B, your eyes, E, are about 0.01 miles above the water. Ooh, I might have to, redraw all this. At point B, you can no longer see the fireworks because the curvature of Earth, the radius of Earth is about 4,000 miles. And FE is tangent to Earth T, so right angle there. Find measure of arc SB, round your answer to the nearest tenth. So these are two different angles that we're going to be referring to. Remember, if this is 4,000, we get to add these little bits to them. I don't think I have to redraw anything, but I just have to emphasize what these lengths are going to be. This is the hypotenuse of this triangle here. And this will be 4,000.01. So, sorry, I have to do this with my mouse. 4,000.01. And this arc here, I'm going to add the 0.2, but this will be 4,000.2 in another triangle. 4,000.2 0.2 miles. These are hypotenuses of these right triangles with that leg of 4,000. I have to find these two different angle measures. I'm going to add them together, and because it's a central angle with C as, I guess, the core or center, I will add those two angle measures together and do that. So I'm going to call this, well, I'll call them what they are, what they seem to call themselves. So on number 24, I'm going to find the measure of angle FCT as the inverse cosine. It's once again cosine of 4,000 over 4,000.2, and that'll be something. And the measure of angle ECT will be the inverse cosine of 4,000 over 4,000.01. These will be very small angles, guys. Once again, not drawn to scale. It says as much there. These will be even smaller than the 1.4 degrees, but we're going to add those two together. So on my calculator, you can't see it, but I'm going to do 4,000 over 4,000.2 for the first guy. That's I'm going to give a couple decimals, 0.57295 degrees. That is a degree measure. I am in degrees on my calculator as well. These are not radians. And then the even smaller angle, 0.01, this will be 0.12812 degrees. Now I'm going to be adding one with the other because this will be the final result of, sorry, I'm trying to recall these values. This plus, let me show you my calculator so you don't look like I'm just doing nothing. Okay. So I'm doing this plus, I'm going to keep the exact ones in here though. Oh, let's do this. Let's do this previous answer 0.2 plus the previous answer made. Oh, what did I do? Domain error. Oh, I did not close the, darn it. This is taking too long. There we go. I should just type in the rounded values. No one's going to care. All right, so this is the degree of both of those added together. So measure of angle, hopefully you see the number. You can pause this. I'm going to go back. Measure of arc SB, is going to equal the measure of angle FCE, which is going to equal those two, measure of angle FCT plus measure of angle ECT. So those two added together give me about 0.70106 degrees. I'll just do 0.7 degrees once I got everything rounded right. So what was the question? Find the measure of arc SB. We just did that. So that's how much coverage of the Earth, 0.7 degrees out of the whole 360 that the arc is. All right, number 25. Mathematical connections. In the diagram, ray BA is tangent to circle E. Write an algebraic expression for measure of arc CD in terms of x. Then find the measure of arc CD. So they first want to ask in terms of x. So the measure of arc CD, you'll notice there are two arcs there. Given that there's the tangent, then those two make up part of what's 360, and we subtract those from the overall 360. So 7x plus 3x taken away from 360, we get 360 minus 10x. Here's the measure of arc CD in terms of x. So let's solve for x, and then we'll substitute that into there. So to do that, let's do that setup. 40 is going to be half of 7x minus 3x. So 40 is half of 4x. Half of 4x is easy enough to do. I don't have to double things. I'll get 2x. So x will equal 20. So if x equals 20, the measure of arc CD is going to be 360 minus 10 times 20. Sorry about that. Measure of arc CD is 360 minus 200. So the measure of arc CD is 160 degrees. And that looks like that would be a good to scale thing because it's not quite 180 like the diameter thing would show. It's not quite a diameter, so not quite a semicircle. All right, number 26. Mathematical connections. The circles in the diagram are concentric. That means they share the same center. Obviously different sizes. Write an algebraic expression for C in terms of A and B. Well, here... Oh, never mind. I was going to say C should be the same as B, but that's actually not necessarily the case. That's actually not the case. It's not a central angle. Got it. So let's do this. I'm going to write this angle as X briefly here. I know we're going to do it in terms of A and B, but I'm going to write this angle out just so you know what we're talking about. So for number 26, we know that this inscribed, and this is one of the better ways I can talk about inscribed angles, right? X is an inscribed angle to C, straight up. It is. It's an inscribed angle to C. But we can first relate it in terms of being half of B minus A. So X is half of B minus A. But X, if I do two X's, I also get C because X is half of C. So let me write it that way. X is half of C. So all told here, what's going on? I can double both of these. I can double this one. I get 2x equals B minus A. And I can double here. And well, actually, here, let's just set them equal to each other. Set these equal to each other. I get half of B minus A equals half of C. And if we double both sides, we're going to get B minus A equals C. Or C equals B minus A. That almost doesn't make sense. Well, no, okay, so it does make sense. But to you, you'd probably say, wait a second, why is it smaller? Why is it smaller than that? You have to remember that these aren't lengths. These are measures. These are measures. So B is a bigger measure. It covers more of this circle, this smaller circle. This, like, it's not 180 degrees, but, you know, let's say it's 150. If this is like 150 degrees, C covers less of its own circle. C might be closer to like 100 degrees, for example. Remember, this is a bigger angle. This is a bigger angle than this is right here, right? Smaller central angle, therefore smaller measure. How much smaller of a measure? Take out A's measure. So it does make sense for that to be the answer. Okay, let's keep moving forward. Let's go to number 27. Abstract reasoning. In the diagram, ray PL is tangent to the circle and KJ is a diameter. What is the range of possible angle measures of angle LPJ? Explain your reasoning. So it's going to be less than 180. Oh, the angle. It's going to be less than 90, I guess I should say. So here's the thing. Whatever tangent to the circle. If it's tangent to the circle, then this is 90 degrees here. This is 90. I'm wondering if that matters for us to say anything there. I just... and P can't be parallel to this, so it's going to be... So this has to be... This arc has to be less than 90 in and of itself. And then this arc... I'm trying to think of how they want us to say if it's like... It's definitely less than 180. It says the range of values. What is it definitely more than besides 0? Excuse me, less than 90. But what is it besides 0 there? Because the most extreme you could get, right? What I'm thinking about is the most extreme you could get for something like this is if this is center right here. If P is like, let's say it's tangent to it. It's tangent to it right there. Then this thing's going to be 90 degrees. But the more you stretch out, the lesser than 90 degrees it gets. Boom. And lesser than, to the point that it can't be 0, but it can go so far out that it could be like 1 degree. So it says explain your reasoning. I'm kind of explaining it here. The closest it can get is right next to tangent to it, which is 90 degrees. But the measure of angle LPJ has to be somewhere between 0 and 90 degrees. That's as best as I can say. LPJ. Because this could be so far out as an angle that hitting this diameter here and this can can really squeeze that angle measure, but it can get so close to the circle that it can be close to tangent to the circle. And tangent to it would be 90 degrees. That's me saying it out loud. I'm not really typing anything there. But that's the range of values it could be. All right, number 28. In the diagram, AP is any chord that is not a diameter of the circle. So not the diameter. Line M is tangent to the circle at point A. What is the range of possible values of x? Explain your reasoning. The diagram is not drawn to scale. So once again, it's not a diameter, but let's say it's one of those indirect proofs. Let's say, for example, it was the diameter. If it is the diameter, then you're talking about a semicircle of 180 degrees, which means x is 90 degrees. But this is not a diameter. This is not drawn to scale. It can be any chord that's not that. Oh, that's weird, because then it can be, hold on, A, the coordinate line M is tangent to this point at circle A. So it could even be here, right? It could be like AB here, and then x could be this big. So x can be anything as huge as going all the way over here to basically a full 180 degrees, but not quite 180 degrees. It couldn't be 90, and then it has to be greater than 0. So this is kind of a thing. X can't be 90. It can't be 90. It can't be 180. It can't be 0, right? I mean, I could have said the same thing here. It can't be 90, can't be 0. But I'm really saying it can't be 90. And it can't be a full straight angle because it has to be a chord, not a single point. And it can't be 0 because it has to be an angle measure. So x has to be somewhere between, either between. So I can write this two different ways. I can either say it can be between 0 and 90, and then, or between 90 and 180. Or I could also say it can be between 0 and 180, but not 90. Like that. X cannot equal 90. If it was a diameter thing, then it would be 90 degrees. Otherwise, it can fit anywhere within that range. It didn't say that it needed to be a minor arc, so I'd assume that you can do anything within that would make it reasonable in that way. I think that's just how I'd work it out. I don't even know if I have to say the greater than 0 part. You know, I think we're assuming that all angles are positive numbers. So I don't even know if saying the 0 part's even relevant, but I'll go with it. All right, number 29, proof. In the diagram, JL and NL are secant lines. JL and L are secant lines that intersect at point L outside the circle. Prove that measure of angle JPN, where's that, is greater than measure of angle JLN. Here's JPN, here's JLN. Because it's bigger. Because the farther out you go, the lesser the angle would become. I could say this, we're doing these formulas, right? Measure of angle JPN, because they have the same intercepted arc things, which is cool. So measure of angle JP, it's not a central angle, but it's half the sum of arc JN, measure of arc JN, plus measure of arc KM, like that. And the measure of angle JLN would have the same intercepted arc parts, but you subtract them. So measure of arc JN minus measure of arc KM. And assuming that these are both positive in that way, this thing here, then this would have to be greater than, because here you're adding a positive number, here you're subtracting a positive number. I think that's just kind of a conclusion. I wonder if there's a way that I can kind of write more on that in that way, but that already kind of gives me the working concept that should work. I just say just because the measures are positive. With everything positive, this must be bigger. So yeah, therefore bigger. Bigger, smaller. It's like, what's bigger? 5 plus 3 or 5 minus 3, right? As long as you're adding two positive numbers added or two positive numbers subtracted. So I guess that's the way I'd go about it, like that. It's not really a proof, but it's it is. I just didn't write it all. All right, number 30, making an argument. Your friend claims it's possible for a circumscribed angle. That's the one with the two changes. I already want to draw it because I'm sure I'm going to have to do something with it. So a circumscribed angle, like this, it's possible to have the same measure as its intercepted arc. Is your friend correct? Explain your reasoning. Which one counts as the intercepted arc? Are they talking about the bigger one? If they're just talking about that one, or do they mean that whole difference of the two thing? I'd assume they just mean the bigger one. Maybe they don't. Maybe they mean the smaller one, because it won't be possible to be the same size as that one, right? That's just not going to happen. So they probably don't want this one. Is it possible for them to be the same? Yeah, because if this arc here is about this central angle, this isn't drawn to scale. If this central angle was 90 degrees, then its arc would be 90 degrees, and this could also be 90 degrees as well, right? It's possible for these two add to 180, right? X, if I call this X and this Y, X plus Y equals 180. For what value does X equal Y is the question. Let's substitute X for Y here. If X plus X equals 180, then 2X is 180 and X equals 90. So the way for it to be possible, assuming they're talking about this intercepted arc for that central angle, is by going by that format. And in fact, that's probably the way I should have been doing some of those other problems when they've been talking about this guy. I've been saying it's 360 minus. I could have been doing a 180 minus for those ones, but they probably wanted me to. And I probably missed the mark on that. I was probably not paying attention to them asking me to do that. So yes, if angle is 90 degrees. Sorry for the syntax being kind of bad. Number 31, reasoning. Points A and B are on a circle, and T is a tangent line containing A and another point C. Points A and B are on a circle, and T is a tangent line containing A. So I'm going to put A right here so I can make a tangent line like that. Let's call it T. And it contains another point C. So here's C. Here's the line T. Draw two diagrams. Oh, so there. Draw two diagrams that illustrate the situation. Well, there's one. I don't know what a second one is that they'd want, but here's one of them. And oops. Here's another one. Whee! I don't know what they want for a second one. Do I just move B in a different spot? I don't know how they want a different kind of drawing for this. I really don't. This is one, any version of this drawing I hope will do. I hope that right here works. Boom, boom, boom. I lost my T. There it is. All right, two drawings. Great. I don't know. Maybe I can put B over here. All right, that's part A. Part B, write an equation for measure of arc AB in terms of measure of angle BAC for each diagram. Got it. So do I need to draw a chord? Let me kind of make a thin, I'm going to make a thin chord out for these ones. So now I made one acute and one obtuse. I think that's a way to say two different drawings. I hope that helps out. So here, measure of angle BAC. Wait, write an equation for measure of arc AB. So measure of arc AB in this one is going to be like a smaller angle here. Remember, BAC is half the measure of it. So measure of angle BAC is half the measure of its intercepted arc. So write an equation in terms of BAC. We got to double it. Measure of arc AB is double the measure of angle BAC in the first one. Now, in the second one, this arc AB being a minor arc, it is a minor arc, but BAC is this angle here. So you'd have to do 180 minus it. So it's the same idea, but we are going to double 180 minus measure of angle BAC. So one's kind of a bigger angle, one's a smaller angle, like that. Maybe that's what they wanted me to do. Part C, for what measure of angle BAC can you use either equation to find measure of arc AB? Explain. These ones appear to be for obtuse angles. This is for obtuse. I didn't really write them parts A, B, C. I've been kind of not in my game here. And this is anything acute, or I guess a right angle. So this is also obtuse or right. Once it's a right angle, it's not going to matter whether you do the double or the 180 minus double, because it's just going to be that same 90 degrees that you're doubling. So acute or right, obtuse or right seems to work for that. All right, number 32, reasoning. Triangle XYZ is an equilateral triangle, and I can draw one of those. 32. Let's do a Boom. So XYZ. I don't know what else they're going to say after this, so let's find out. Equilateral triangle inscribed in circle P. I don't know if I need the drawing, but I'll at least need the drawing to explain stuff to y'all. All right. I don't know where the center is anymore, though. It's probably closer to here. So circle P. AB is tangent to circle P at point X. I don't know which one's the B, though. Maybe it's not really, like, okay. Let's call this, they said segment AB, so it has, like, endpoints. So AB is tangent at point X. BC is tangent at point Y. Okay, so I have to extend this out more. This drawing might get a little big. So I have to, like, do another tangent here. Basically, I have to do another equilateral triangle. It's basically going to be a bigger version of one. Let's see if I can make that happen. And I'm sure they're going to ask me, so, like, what kind of shape is it or something. I don't really know. But let's do another equilateral triangle. This time I'm going to make it bigger and basically hit at those points. Yeah, this will get kind of big. So it's going to look more like this. This might actually be pretty good. Not quite. Yeah, I'm discovering without even finishing reading the problem. So I'm like, okay, we got to do like this kind of thing. At least this time I can make it right. It's probably easier to do with pencil, even though you probably want tools. So it's probably like this. AB, which one's tangent to Y? B is Y. So this has to be B, this has to be A, and I guess AC is tangent at point Z. So here's C, ABC, tangents, all that. Draw a diagram that illustrates it. I just did. Classify ABC by its angles and sides. Justify your answer. Well, I could tell you it's going to be an equilateral triangle just by the way things have to measure themselves out. But if this was equilateral to begin with here, then these are all 60. And if these are all 60, then they're intercepted arcs, right? This is an inscribed angle. Here's an intercepted arc of 120, 120, and 120. Well, B, for example, measure of angle B is going to be half the measure of this big guy of 240 minus the small guy of 120. Minus 120, which is half of 120, which is 60. So B is 60 degrees. You're going to find out that A will be 60 degrees and C will be 60 degrees. They all follow the same exact thing. So triangle ABC is also an equilateral triangle because it's equiangular. So triangle ABC is also equilateral as it is equiangular using the theorems. Anyway, yeah. So equilateral, equiangular, same kind of thing. But that's the drawing. That's what it'll look like. Okay, got 8 more problems to go. Let's go to number 33. We got to do some proofs, it looks like here, at least another proof. So 33, proving a theorem. To prove the tangent and intersected chord theorem, you must prove 3 cases. Wow. Part A, the diagram shows the case where AB contains the center of the circle. Use the tangent line to circle theorem to write a paragraph proof for this case. Tangent line to circle. Tangent line to circle. Well, there's going to be a 90-degree angle measure, but I don't know. I have to think of what this actual proof thing was. It says that it's half the measure of its intercepted arc. Yeah. Okay, so I'll just state that measure of angle ABC, or BAC, is 90 degrees. 90 degrees because a diameter / radius intersects a tangent perpendicularly. Also, measure of arc AB. This is tough for calling it measure of arc AB because normally semicircle should use 3 letters, but measure of arc AB is 180 degrees no matter which way you spin it because it is a semicircle. Therefore, measure of angle BAC is half that of measure of arc AB. So let's write that down there. I know the way that I'm typing it kind of makes it tough to read, but that's half of that. That's how I'm going to work out saying it, at least. All right, that's part A. Let's go to part B. Draw a diagram and write a proof for the case where the center of the circle is in the interior of angle CAB. Oh, they said CAB. All right, so let's do the same thing. They said in the interior of. The center's in the interior of. Whoops. Why don't you plot yourself a point there? Kind of a big old center. All right, let's do tangent and a chord where they said it's in the interior. The center's in the interior like that. So CAB. They said draw a diagram and write a proof for the case here. Well, could we just do this? Because this seems similar to what I did in section 10.4 at the time for another kind of proof. Could we split this up into two parts where we have the 90-degree angle plus the measure of this angle, and this is an inscribed angle here? So maybe I can keep this one. I'm going to call this D. I'm just going to add a new point name and just do the same semicircle thing. So keep what we just did before. Find the measure of angle DAB as an inscribed angle. I'm not doing a paragraph proof. They did say write a proof. But measure of angle DAB is half the measure of arc DB. And we already know that the measure of angle CAD in this case is 90 degrees based off what was above. So the measure of arc AD is also 90 degrees. So the measure, let's see, how do I say this? And the measure, because I'm adding angles, now I'm adding angles with arcs, even though they're the same measure. Well, they're not the same measure. This other one's 180. So let's see, measure of angle CAD is 90 degrees. So the measure of arc AD, I'll just call it AD. AD is 180 degrees. You double it. So what I have to do is add 180 with this amount and say that that's half that angle. I don't have to say 180 specifically. Do I? I just have to say it's half that other one. No, I don't have to say specifically 90. We just proved that one's half the other. So I don't have to say 90. I think I just got to say half the measure of arc AD. I think I was getting mixed up with, I'm adding numbers with variables. So the measure of angle DAB plus the measure of angle CAD is going to be the measure of angle CAB, the one that we're looking for. And the measure of arc DB plus the measure of arc AD equals the measure of arc AB. So therefore, with those halves in place, let's take half, half, and half. So the measure of angle C, this is like a substitution thing, measure of angle CAB will be half the measure of arc AB, like that. So it still works in that way. It's still half that measure. So basically what we did was we found out that this angle is half of this arc. We proved already this angle is half of this arc. So when we add these angles together, add those arcs together, then this angle is half of this arc there. Now, I want to call it not AB, but ADB, I guess. Let's call it ADB because we need to call it kind of a major arc. So ADB here and ADB there. So kind of more of a major arc like that. Okay, they want to do one in the exterior, center in the exterior. So I want to do the same drawing stuff, copy and paste. The difference is we'll have a subtraction. This is why it reminds me of the other problem we did in 10.6. I just got to bring it to the side. Let's call this part C. I'm going to do literally a lot of the same stuff here. I'm just instead going to call this part C. Drag this down a little bit more. Like that, I suppose. And over a little bit, I suppose. So part C, let's now change it so that this AB is now on this side, like that. So it's going to be a minor arc. And then there's still the right angle in the subtraction and such, only now this arc is right here. Whoops. This arc that I need is right here. Let's work out the same things. Measure of angle DAB is still half the measure. Oh, shoot. The center moved. No, move the center. Measure of angle DAB is still half the measure of this arc, DB. The measure of angle CAD is still half the measure of arc AD. I can now call this ABD now that I kind of have that point there. So I can call this ABD. But that was proved the first time around. And now we're going to subtract. We're going to do measure of CAD minus measure of angle DAB. Measure of angle CAD minus measure of angle CAD, DAB equals measure of angle CAB right there. That's good. So subtract those and you get that angle. Measure of arc ABD. Measure of arc ABD minus measure of arc DB, what we had before, equals measure of arc AB. Now it's a minor arc, so we'll call it measure of arc AB. So you can put the halves in front as well if you'd like to, like last time. That's not going to necessarily change too much, but just by substitution here, these are going to be equal to each other as well. Measure of angle CAB will be equal to half the measure of arc AB. And that's the final result there. So they all seem to work. For me, it was more on the inscribed angle concept, and I mentioned it at the time what it looked like. So I'm a believer either way. Okay, number 34. Oh, I see a proof down below. Number 34. How do you see it? In the diagram, television cameras are positioned at A and B to record what happens on stage. Okay? The stage is an arc of circle A. You would like the camera at B to have a 30-degree view of the stage. So this is 25. This is what they mean for the stage 30 degrees there. Interesting on how they kind of speak on where they mean the 30 because they say of the stage. Should you move the camera closer or farther away? Explain your reasoning. But... well, let's start. The only thing I don't know is because they already have numbers there. Now, let's say we use these numbers the way that we kind of have been. We'd say 25, like there are no variables. 25 is half of 80 minus 30. Oh, and it is 80 minus 30. So 25 is half of 150, or 50, excuse me. 25 equals 25. So that part pans out. I thought they were going to say one's bigger or smaller than the other. So we would change something based on it. The stage is an arc of A. You would like the camera at B to have a 30-degree view of the stage. Should you move the camera closer or farther? Are they saying, wait, is this the stage? Television cameras are positioned at A and B to record what happens on stage. The stage is an arc of circle A. Is this what they call the stage? If this is what they call the stage, you'd want the camera to be closer, right? So that's the only part I don't get is I guess they want that part to be close. I guess they'll just say closer. I don't know if I understand the problem in what it's asking. I guess you'd say you'd want it to be closer based on what's there. If you move it closer, then it shrinks the angles. 80 minus 30 is 25. 25 is there. You want it to be 30 degrees. I guess I'm not sure what they're really asking for. Let me pause and think about it. Okay, here's my thought of the problem now. Let's look into the drawing. I think what they're saying is they want this to be 30 degrees. It's 25 right now. I was assuming that would be fixed. So they want this to be 30 degrees. If they want this to be 30 degrees, then we need to figure out, because this is going to be 80, period. They said this is the staging area. A has it, and this is what they want. So keep that the same. What new X would we need for this to happen? And if we change it and see what X is, basically, how would that be closer or farther? So I'm going to work off it like that. So let's try this instead. Let's try 30. 30 is half of 80 minus X. Minus some new X. We have to figure out what that X is to determine whether we should be closer or farther. So, let's double everything. Let's erase everything. How about that? Let's double everything. We get 60 equals 80 minus X. add x to both sides, subtract 60 from both sides, and we get 20. So if x is 20 degrees, then this goes from 30 to 20, and 30 to 20 is a smaller arc, which would mean you'd have to be closer. You need a wider angle. You need to be closer to this to capture that. So you would want to be closer. Wider angle, smaller, minor arc. Not minor arc, but smaller arc. They're both minor arcs. Okay, I think that's what they wanted. It's just troublesome because they already have drawings there, so I didn't know, or numbers, so I didn't know which one they wanted. All right, number 35, proving a theorem. Write a proof. I had my own version of the proof, but we'll see if we can come up with an actual one. Write a proof for the angles inside the circle theorem. Given chords AC and BD intersect inside a circle, prove that measure of angle 1 equals half of measure of arc DC plus measure of arc AB. So my version of the proof was move the angle outward and you have an inscribed angle bit. I was kind of a fan of that one. Maybe here we can talk something about similar triangles and do something off that. I'm actually not sure quite yet. Let's copy and paste this thing over and see what we can think about. And I don't always go for 2-column proofs in these cases. It seems more like a mathematical based thing that we do to make this happen. I'm wondering if inscribed angles are the way to go. Maybe we can talk about how they both share this arc BC in this bigger way. I don't really know. How about this? We have, because they drew this, because I'm thinking about why they drew this. I was first thinking of the arc. Let's think of this chord. Why do you think they drew this? I think we can use this to talk about these angles. Like this angle, it's an inscribed angle to this. And this is an inscribed angle. You know, this is an inscribed angle to that. I think we can do something with those two. So let's think more in those terms. Let's look at measure, like right here, measure of angle ACB right here. So that guy, inscribed angle, right? Measure of angle ACB, that'll be half the measure of arc AB, measure of arc AB. And if you look at this other one, we have this guy, measure of angle DBC, you call it? Measure of angle DBC is half the measure. See, the only thing is this is great for a theorem and stuff. It's just not going to help you remember the formula. So measure of arc DC, or should I say CD? I don't know, it doesn't really matter. Now, with this one here, that measure of angle 1, you know, we have... I'm trying to think of the remote. Yeah, so it's a remote exterior angle to these two. If you imagine this, what's in red, to be... Look at the triangle that's here in red, right here. The triangle. One is an exterior angle to this triangle with those two angles right there and right there, the ones that we just found. They're not congruent, but we can work off of that. So the measure of angle 1, the one that we're dealing with, is going to be the sum of those two angles. Measure of angle ACB plus the measure of angle DBC. And if that's the case, oh, perfect. We can do a substitution. So therefore, the measure of angle 1, let's use black, that'll be 1/2 the measure of arc AB plus the 1/2 the measure of arc DC. Therefore, oh, looks like they put DC first. Let's do that then. DC and AB. Therefore, if you factor measure of angle 1, factor that, we have measure of arc DC plus measure of arc AB, like that. So it kind of works out through a substitution thing, if you will. That's what I did in this other part. I substituted here for that and here for that just by using that chord. The fact that they drew the chord really helped me out with the problem. I didn't know what to do otherwise. Looks like it works out. All right, let's keep moving forward. Let's look at number 36. Thought-provoking. Oh, I see 2 proofs after this. No fun. In the figure, lines BC, or BP, excuse me, and CP are tangent to the circle. Okay. Point A is any point on the major arc formed by the endpoints of the chord BC. Label all congruent angles in the figure, justify your reasoning. Okay. If it's tangent to... Let me go back and look at... It's something I should already just know. I want to look at what they said for the tangent part. Like, okay, here. I'm going to draw a center for a second. I'm not going to go back. I'm going to do this myself. I'm going to imagine some X right here and some Y, because I've done this before. We should know that in this case, this isn't part of the problem yet. I just want to make sure I got my formula stuff going on. x plus y is 180, so that y angle is 180 minus x. That's the central angle. But that central angle also would represent the intercepted arc measure here. So whatever that x is, that arc BC, that angle measure is equal to. So A is the inscribed angle measured to that one. Okay, that means a lot to me. So what I'm trying to, sorry, I'm talking to myself, and now you get to hear, I'm talking very out loud, but you're like, what? What? So, okay, I'm piecing it together. I don't need the central angle anymore, but measure of angle CPB, if I'm looking at it, I got to erase what I write in a second, is equal to the measure of arc BC, and it's equal to double, that measure of angle A is an inscribed angle, so double the measure of angle CAB. So, okay, let me erase all those X things. So I didn't really utilize that last time, the whole 180 minus. I wasn't using that. I thought they were going to ask different questions about the quadrilateral, not about the arcs. I don't know if they made that connection for me, but I didn't make it for it. And I kind of feel about not doing that earlier. So that angle P and angle A, they ain't the same. They ain't the same. One is double the... Wait, they look congruent, though. They look congruent. CPB, I said 180 minus, right? Hold on, let me think about that again. This X was this X here, and 180 minus X was the Y, and that X will be two of those X's. It takes two CABs to equal this. It takes 180 minus... Oh, I'm sorry. It doesn't equal measure of arc BC. It's 180 minus measure of arc BC. Let me fix that then. This would be... Sorry, this is me. I've never seen these problems before. So it's not measure of arc BC. It's 180 minus measure of arc BC. 180 minus. All right, so there's that. Those are two things in one. That didn't really do too much for me just yet. Angle PCB. Oh, this guy is half of that arc as well. Okay, so I don't know if anything I did is helpful yet, but here's what I do notice. I have an angle right here, which is going to be half the measure of this intercepted arc. Okay, hold on. I see some that are the same. Measure of angle PCB is going to be 1/2 the measure of arc BC, and so is the measure of angle CAB. You know, I said two of these equals one of those. Ooh, I wrote this part wrong anyway. I'm sorry. I'm not editing this part out. I'm processing. I'm working this part out the way that I want to, so you're gonna have to deal with it. This is me trying. Measure of arc BC. This is the same for the angle that I said before, measure of angle CAB, because that was an inscribed angle that way. I'm basically seeing a bunch of inscribed angles. And then this one down here. I have this one down here. I thought they were going to talk about measure of angle P more. I don't think so anymore. This guy is also half the measure of that intercepted arc there. So measure of angle CBP is also half the measure of arc BC. So those are all the same. Same. I don't know if any other ones are. I was looking at that measure of angle P. It looks different from A. There's no reason I could guarantee it was the same. So those ones look the same. I don't know if there are any other ones, but those three look the same. Yeah, I guess that other one is just a 180 minus and it doesn't work out. I thought they really wanted to get into that 180 minus stuff, but no. This was all about the inscribed angle stuff that I mentioned before, though, basically, right? They all share the same intercepted arc. This one, and this one, and this one. They all share the same intercepted arc, therefore they should all be the same angle. I don't see anything else that should be the same besides that. All right, 4 more questions. Number 37. We got a proof. Use the diagram below to prove the angles outside the circle theorem for the case of a tangent and a secant. Then copy the diagrams for the other two cases on page 607 and draw appropriate auxiliary segments. Use your diagrams to prove each case. That's a lot of stuff. I don't know what they want us to do. Let's see. Let's first copy this one down. And I'm going to copy the ones down on 6 or 7. I'm going to pause and find what they are, and then I'll bring it back with all those. So let me pause for you guys right now. Give me a second. Okay, so these other two, this is basically all 3 of those theorems. I copied these other two down here. It's all the ones that say that this is half of this minus this is half of this minus this, and of course this one is half of this minus that. But they talk about drawing an auxiliary line, so I'll make sure to do that for these other ones. Probably something like, I guess I'll make it blue as well. Or no, that's blue right there, so I'll do like green. But I probably need to do a point. Do I need to do that? Whoops. Do I need to make like that an auxiliary line, or do I make that an auxiliary line? I'm not quite sure yet. We'll see. I'll keep it there, and then we'll see what we do with it later. I'm not sure. So here, they said, it basically proved that this is half of this minus that, right? The original theorem is measure of angle 1 is half of measure of arc BC minus measure of arc AC. Okay, that's the idea. We have to get that proven. I would say to do it, the reason, so you always have to ask, why do they draw an auxiliary line? Last time we saw it based on angles. The line made angles. Now this is an angle, but that's not with a tangent line thing or an inscribed angle. That doesn't make sense, but this one does over here. So I have an inscribed angle for this, and this is an intercepted arc we need. And then this one can, I guess, for this one. So I can talk about intercepted arcs for these inscribed angles, and we already proved this one here before, so I can use it. Inscribed angle we proved in the last section. So looking at the purple, if you look at measure of angle BC, measure of angle 2, that is 1/2 the measure of arc BC, and we can call this, I guess I have to use the letters, measure of angle ABC as half the measure of arc AC. So how do I say that this, because I got to find out how to say 1/2 of this minus this minus this. So how does 2 minus ABC work itself out to equal 1? Oh, how about this? We just did this last time as well. This is a triangle right here with this angle, and here's an exterior angle of 2 on the outside of these two remote interior ones. So I could say that the measure, let's do this in red, the measure of angle 1 plus the measure of angle ABC equals the measure of angle 2. But I want to solve for measure of angle 1. So let's subtract measure of angle 1 equals measure of angle 2 minus measure of angle ABC. So if I move these ones down and out of the way, let's kind of keep going here. I don't know what I want to do with that auxiliary line yet. If this is the same kind of process, I can probably do some copy paste. Not fully, because they're different letters. But now I can substitute. Measure of angle 2 is 1/2 measure of arc BC. So 1/2 measure of arc BC, and then minus this one is 1/2 measure of arc AC. See, I've never proved these before. I've just kind of spoken on logic. So measure of angle 1 equals this guy. Factor out the 1/2, you have measure of arc BC minus measure of arc AC. All right, that can be a proof for that one. That's just 1/3 of this overall problem. So that works. Okay, let's talk on this one here, make the same concept on auxiliary lines, but we need to make sure that arcs make sense. So last time they drew an auxiliary line connecting, making this arc with this angle and the arc that's formed here. So would it make more sense? I don't think it would make any sense to do something right there. I don't know what that gives me for an arc, so I'd probably right here. But last time they gave a number to a number to an angle. Do I have enough letters? I guess these need numbers because... Ooh, I don't know where to draw that thing. How many numbers can I provide? Can I just make multiple numbers up? Can I call this a 1 and a 3? Because they didn't give me other points. So if they're going to do that, I'm going to put numbers on these. I think we can do the same thing. This plus this equals that. So this equals that minus that. And then I could say what the arcs are for the inscribed angles. So with this one, literally we're going to do the same stuff here. But we just have to make sure we have the numbers. So we're going to prove that this equals that minus that. I'll do that last. Let's start with the sum. 2 plus 3 is 1. Measure of angle 2 plus measure of angle 3 equals measure of angle 1. So measure of angle 2 equals measure of angle 1 minus measure of angle 3. I gotta sneeze. Okay. So subtracting those. Now let's write measure of angle 1 as half of... Yeah, that's the thing. So half of this. That's why they need the Q. Measure of angle 1 is half the measure of arc PQR, and the measure of angle 3 is half the measure of arc PR. So now that we can substitute, measure of angle 2 is that minus that, so half of measure of arc PQR minus measure of arc PR. It's nice when they kind of have the same proof concept over and over, so I can just do it over and over. Measure of angle 2 is half of factor, measure of arc PQR minus measure of arc PR, like that. So there's that one out of the way. We have a third one to do. In the third one, we have to draw another auxiliary line. We have measure of angle 3 as this guy, which we got to find that minus that. So we got to draw an auxiliary line either, I guess not there. Let's just do green. What if I go here? Do I draw 2? Probably not 2. I think I just need 1. It won't matter if I do this or that. Is that how I do it, though? Where's the inscribed angle? Okay, this angle has this intercepted arc, and this inscribed angle is that intercepted arc. So I'm going to do that same kind of thing, and I'm going to give them angles 1, and I guess 2. In that kind of way as well. Hopefully that kind of works itself out. So let's do that. I think that works. So now measure of angle 3 plus measure of angle 2 equals measure of angle 1. Again, that's the exterior angle theorem in play. That plus that equals that outside part. Measure of angle 1 is half the measure of arc XY. And measure of angle 2 is half the measure of arc WZ. Measure of arc WZ. I hope I can throw numbers out there. They did for the other problem, so I'm just going to do that. Oh, I didn't say, hold on, I didn't subtract, let me go back. I didn't subtract measure of angle 2 on here yet. So measure of angle 3 equals measure of angle 1 minus measure of angle 2. Okay, so now let's substitute. So measure of angle 3 is 1/2 measure of arc XY minus 1/2 measure of arc WZ. Therefore, factor out the 1/2, measure of angle 3 equals 1/2 measure of arc XY minus measure of arc WZ. There we go. Okay. All right, long problem. Let's go to number 38, where there's another proof. Let's see if 39 and 40 are proofs. No, doesn't mean they're going to be easy. Number 38, proving a theorem. Prove the circumscribed angle theorem follows from the angles outside the circle theorem. The circumscribed, oh, that one with the tangent lines. 38. I kind of did that one already. I did it by accident, but it should still apply. So I was doing it in that other problem where I was discovering what goes where, right? I think so. I feel like that's what they're asking. So let's do like a tangent line thing. It's circumscribed angle means like a couple tangent lines here and here, right? And then what we did, you know, what I was doing before was, because they did it too, right? Drawing the central angle bit. So what we could do is, with the central angles, it kind of helps make sense of what this angle thing is. But the measure of angle, I don't know, just call it 1 or X or whatever. I don't know. We have, well, I need some letters. Let's call this A, B, C, center C. So we have this guy here. Remember, this is the same as this intercepted arc. So the measure of arc AB equals the same as the measure of angle ACB. Just keep that in mind. Because the measure of angle 1, I hate that I'm using a number on that one now instead of just a letter, but the measure of angle 1 plus the measure of angle ACB is 180. So the measure of angle 1 equals 180 minus the measure of angle ACB. And you can also substitute the measure of arc AB into there. So the measure of angle 1 equals 180 minus the measure of arc AB. So I got to that stage. There was also something that I showed that said, let me think about this. I want to think what they're asking me to do suddenly now. Because, see, I wasn't using this so much before. I should have been using this in the earlier problems, and I totally wasn't doing that. Well, how about this? Here's how I was doing it before. Remember what I was doing before? I said something like, I don't know what this thing is, but I can do 360 minus this to figure that out, or the other way around. So how about this? Let's call the measure of arc AB, right? Say, I know what this is, and I got to figure out what this guy is. Because half of this minus this should give me that. So I could also say, I would need a whole nother point there. Do I call it a D or something like that? Actually, I don't even need it. I just need an expression. Whatever this is 360 minus that, measure of arc AB. So I could say measure of angle 1, I'm going to keep this. This is important. Measure of angle 1 equals half of, and I take that bigger guy, 360 minus measure of arc AB, half of this minus that, minus measure of arc AB. Because this is how I was doing the problems, and it was kind of wrong for me to do that, but now it's too late. Whatever. I still solved the problems. They still worked out. So half of, and these double up. 360 minus, I said you subtract it twice. I was using that at the time. And when you distribute the 1/2 into there, you get measure of angle 1 equals 180 minus measure of arc AB. So you notice that these two connect together. They were for way different reasons that they connected, but they did. So these are the same. And this was using, what did they call it? They said, I have to bring it back. They said, prove that the circumscribed angle theorem follows from the angles outside the circle theorem. So here's the angles outside the circle theorem that I used, and it seems to follow, this seems to follow that. We seem to get the same thing from that. Okay. That's how I'm going off of it. They connect. From in exercises 39 and 40, find the indicated measures justify your answer. Okay, so number 39, we have a diagram. It says find measure of angle P when measure of angle WZY equals 200 degrees. So this whole thing is 200 degrees, and they show congruence on this other aspect here. Let me actually copy paste this thing over. Okay. So this whole thing, I'm trying to curly brace it, but do it around something. This whole thing is 200 degrees. This guy here, and these are congruent, so these arcs are congruent. So let's say that this was an A, and this would also be an A, right? So that also means that this is 200 degrees, by the way. So whatever WZ is, I'll say measure of arc WZ plus A equals 200, and that's the same A as the other one before. So A is 200 minus measure of arc WZ. I don't know how much this matters yet. I'm trying to figure it out. So A is that measure. But there are two of those. There are two of those in the diagram, and when you add the measure of arc WZ, you also get 300. Oh, no, you don't. 360. There are two of those plus the other two. How about I do this? No, that's a subtraction. I just call it 200 minus A, but that won't quite contribute to what we're doing here. If that's 200, then this is 160. How about that? I'll do it like this. Measure of arc WZ, because it's all about WZ right now. Measure of arc WZ is 200 minus A, and measure of arc XY is 160 minus A. Maybe these will cancel out. I think the A's will cancel out here. So the measure of angle P, let's get rid of this. I don't think I need this one. So the measure of angle P is 1/2 of the WZ minus, so WZ minus XY. Yeah, I don't know if the A's really matter. The fact that they're the same is kind of helpful enough. So measure of angle P is 1/2. I think the A's cancel here. Negative A minus negative A is plus A. You get 200 minus 60. 200 minus 160, which is 40. So measure of angle P equals 40. Half of 40. Which is 20 degrees. I don't know. Yeah. I don't know. That's, I think. WX, oh, yeah, WZY is 200. I think. I'm going with that. That was good. All right. And lastly, I don't know if I have to put the A things, but that's just how I worked it out. And lastly, number 40 seems like a diagram to copy and paste, but we'll see. So 40, we're going to get find measure of arc AB and measure of arc ED. Whoa. Okay. Let's hope this one's not too massive. Where is AB? There it is. Measure of arc AB. Let's find that one first. Hopefully finding one will help me find the other or something like that. All right, so AB. So I have a 60-degree angle here, and its intercepted arc, boom, is this whole, if that's 60, then this whole thing here, let's not use the same color, this whole thing here would be 120 from here to here, measure of arc AD, because that angle goes boom like that. So this is 120 degrees. They show this part as 20 degrees. This is 85. Let's see where I can go to. 20, and this unknown AF. I got to work that out. That's a 90-degree angle here. Whoa, there's a lot, guys. There's a lot to dig into here. Let's see which way I want to navigate this thing. There's no inscribed angle from B to C for me to work off of, so I can't do anything there. J, if this is 60, okay, hold on. I'll keep that in mind. Measure of arc AD is 120 degrees. Here I have a right angle. If this is 60, then that's 30 on the J. And it's this arc minus this 1/2 of AB minus J's arc. There are a lot of ways to connect this AF. I need to find out what AF is. I think that's the biggest part. So there are a lot of ways I can come up with it. It's more like a system of equations to use, though. So one of them, if AD is 120, then, gosh, I don't know which way to go with it. If this is 115, then this is 65. So let me start with this one. 65 is half the sum of 85, and then this 20 plus AF. I don't know what measure of arc AF is, but this 20 plus AF is the other arc that needs to add with this one to become the 65. So there's one of them. So let's get that AF by itself. I'm going to double everything. I get 130 equals 85. Oh, I guess this would solve for AF. It's not a system. I can just solve for AF here. I don't know what I'm doing. What's 85 plus 20? 130 is 105 plus measure of arc AF. I thought this was going to be this hard thing to do. Subtract that, measure of arc AF is 25 degrees. That probably could have been found in a bunch of different ways. That's not the answer. But this 25 degrees right here can help me for a few things. I can find the measure of arc AB now using this measure of angle J. I know this is hard to see, but this angle J right here is half of this AB minus the AF of 25. Now J's angle is 30 degrees. It's 30 degrees because this is a right triangle and that angle is 60. If that angle is 60, this one's 30. So 30 is going to be 1/2 of measure of arc AB. Sorry if you can't tell what I wrote. I'm trying to say it out loud, but the diagram is very small to point at or has a lot of information. Minus AF is 25, 25 degrees. So let's double that and we get 60 is measure of arc AB minus 25. So measure of arc AB is going to be 85 degrees. So that should be measure of arc AB. Now we got to find the measure of arc ED. Which one? I lost it. Measure of arc ED. Measure of arc ED. I probably don't have to write that yet. But ED will be... Oh, can we find BC? How can we find BC? It's not an inscribed angle. I was going to use ED with... Oh, ED is going to be really easy. We have 20 and 25 here, and the whole thing's 120. So measure of arc ED is 120 minus 20 plus 25. I guess we don't have to use any central angle stuff now that we got that. It was all about cracking AF, and there's more than one way to find these, I'm sure. Minus 45, that should be 75 degrees. So we should be getting 85 degrees for measure of arc AB and 75 degrees for measure of arc ED. Okay. All right, I think that's all I'm going to land on there, and that should be enough. So, guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. I know I've felt a little under the weather. I'm clearing up a little bit more, but for time's sake, I hope that I was understandable for the majority of it. So thank you so much. 10.6 will be coming up next whenever it does, and take care. I will see you in the next one.